So regular spatial patterns are the opposite, if you wish, of clustering. And what is the opposite of clustering? It's less grouped than spatial randomness, more spread out, more regular, more empty space, the result of some competition or repulsion. So a tree grows in a spot, it keeps other trees of the same species from growing close by. You know, you have animals with their territory. There's no other species anywhere around there. They keep away from each other, respect each other's territories. You know, car dealerships, they don't. They locate together. Okay, but video distribution stores, they spread out. Okay, so these are the kinds of distributions you can look at. You can look at the locations of the video distribution stores, and are they spatially random in a city, or are they grouped together, or are they more spread out than they would be? And that has, of course, policy consequences, because if they're more spread out, there could be all kinds of monopolistic tendencies and things like that. And it's not just for video distribution. This is a very important question in health provision. Do hospitals cluster together? Do they spread out? Do they divvy up the market, or do they compete in the same markets? These are very important issues, and you can get, I mean, you might say, why is he talking about that? You can get a very quick and dirty idea by just looking at the locations of these places as points on a map. And it's limited, but it provides you, in an exploratory analysis, it provides information. And in contrast to the clustering, here we have under-dispersion. So the variability around the mean is less than it would be under spatial randomness. Spatial randomness is Poisson, mean equals variance. Clustering, we saw variance larger than the mean, over-dispersion. Regular, variance less than the mean, under-dispersion. So they're more spread out, more regular than they would be randomly. And how do we get that? We get that by, not by contagion, but by the opposite of contagion, by inhibition. Don't come anywhere near me. Okay? That's the kind of process that we get. And we get this by having a distance cutoff, a barrier, if you wish, that points do not get closer than this particular distance. And so if you impose this, again, we're thinking simulation, we start with a completely spatial random point process, and we're going to kick out points that are too close to me. So we will not allow points to be closer than this given cutoff distance delta, and a characteristic of these inhibition processes is what is called the packing intensity. And this has, again, all kinds of practical repercussions in space allocation. One, I mean, you may not think of it this way, but a packing problem is a very interesting problem in operations research. One of the applications is parking spots. You know, how do you fill parking spots, and how do you make sure you have enough parking spots, and parking spots close by where people need to be? And we won't talk about that here, but I want to make a connection. This stuff is not esoteric points on a square box. You know, there are connections to real life applications where the randomness of these applications gets driven by the processes that we study here. Okay? Where do cars park in a parking lot? That will determine how many spaces we have left that are within 5 minutes walking distance from the mall, right? And that then has repercussions about how we design the parking lot, and so on. The packing intensity is just a summary measure of this. You see the intensity is the lambda, and this is our same circle area. Where does the 4 come from? Delta is now not the radius, but the diameter. And so radius is diameter divided by 2. So if you power that, you get to 4. That's where it comes from. You do have to, refresh your memory about areas of circles and all those things. A particular class of processes that is often studied in the literature is this Matern process, We will see that again in geostatistics as well. There are a general class of types of processes that include both clustering as well as inhibition. The inhibition processes, there's two of them that are used a lot in the literature, 1 and 2, creatively called. Process number 1 is simply a thinned Poisson process where we, as I described earlier, you start with complete spatial randomness and you start putting disks around points and kicking out the points that are in the disk. And that gives us a thin process that will be more spaced out, more evenly spaced out than it would be randomly. And then the other one is a sequential, what is called a sequential inhibition process, which is where you start with randomly putting a point in the box, and then you put the circle around that point, and you do not locate any other point in that circle. But then you randomly locate another point in what's left of the box, so not in the circle. And so you keep doing this, and of course, as you put in more points, it gets more limited where you can put in points. And as it turns out, again, I'll spare you the mathematical detail. The Matern 2 processes tend to be a little more denser than the Matern 1s, and we'll do this in the lab. So each of these starts with a Poisson process of 100 with mean intensity 100. Here we're doing the thinning with the disks. Here we're doing the sequential process. We end up with 33 in this one and 73 in the other one. As you up the intensity of this process, you don't necessarily get more points, but you get more evenly spaced points. Because ultimately with these disks, you run out of space. Right? So if you land these points on the box and you put a disk around them, and you're not allowed to put a new point in the disk, then eventually you run out of space. So this is the kind of thing you get. I'm upping the points that I allocate randomly first to 200, and I only end up with 105 points. Then I push them up to 500, I only end up with 135 points. As we up this, and I don't know if you see this, but this gets more and more regularly spaced. And we can play around with this in the lab as you up these numbers. In the end, it looks almost like a lattice, with just slight, random variability from the lattice. But it basically pushes all the points to about as regular an allocation as it can be. And those are these inhibition processes. Inhibition processes are not studied as much as these contagious processes, but we'll see them too. And I want to close, I won't show any pictures here, with just some concepts so you can connect this with the literature if you read some of the more advanced work. So far we haven't allowed any interaction, not really. We had the contagion in the parent-child process, but there was no interaction between the children. Remember, I mentioned that the siblings are completely randomly, independently located in the disk. Okay? But what if there is interaction? What if there is the probability that an event occurs in a location is affected by neighboring events? And this is expressed and encompassed in these Markov point processes, which is a more modern development, and it has to do with simulation. Markov chain Monte Carlo is a way of modeling statistical processes by means of simulating the processes. So rather than solving complex analytics, you let the computer do the work. And in the 90s, this really took off in the 90s and opened up a whole new class of complicated problems for analysis. These are problems that are basically analytically intractable. You cannot solve this except for ludicrously simple situations which are unrealistic. But the computer allows you to tackle the estimation and the modeling of these kinds of processes by simulation. And what you allow in these processes that you define interaction between the neighbors. The neighbors are defined as being within a given distance of each other. And these processes, as I mentioned early on, are all modeled relative to the Poisson with uniform density intensity of 1. So the likelihood, we'll talk a lot about likelihoods later on. If you don't know what it is, don't worry about it. It's a way of characterizing a distribution is relative to this Poisson. So in the literature, this might throw you off. You know, the normal the standard Poisson distribution, as we saw, is e to the minus lambda, right? In these relative models, it's e to the minus lambda minus 1. And the minus 1 comes from this relative term here, relative to the area, which is the only term that matters in the uniform Poisson distribution if you take a ratio of these two likelihoods. So that may throw you off if you look at some of the more recent papers that, you know, it's Poisson. We know Poisson is e to the minus lambda, but it's e to the minus lambda minus 1. And the minus 1 is because it's relative to, it's actually a ratio. Some of these processes, a Strauss process, we'll look at this in the lab, is characterized by an intensity and power to the number of points, and then an interaction parameter powered by the number of pairs of points. And for gamma less than 1, this is an inhibition process. So by playing with these things, for example, if gamma equals 1, then we just end up with a straight Poisson process. If we let beta be variable, we end up with a heterogeneous Poisson process. And so the approach here, the more modern approach, is to spell out very general models that incorporate both heterogeneity and interaction, and then estimate the parameters of these models from the data. So our goal ultimately would be to estimate what beta and gamma is from the data, from the characteristics of the point pattern. We're not there yet. We'll start to get there next week, and then we'll tackle it more in depth in 2 weeks from now. Then the final set of processes are these general set of interaction processes that allow pairwise interactions with specific functions. These H functions are specific distance decay functions. We'll see similar things when we talk about the variogram in geostatistics, which is also a way of modeling interaction or correlation, if you wish, as a function of the distance that separates 2 points. These are distances between 2 points. The latest flavor of these models, and this is very recent, you know, late 90s, early 2000s, are so-called area interaction point processes, where you see the same general form as this the Strauss process. We have a beta for intensity, and we have a gamma for inhibition. Now, the power of the gamma is not this S, which is the number of pairs of points, but it's a function of the area around the points with a given radius, and this is where our kernels sneak into the process and will allow us to do estimation of these processes. If you printed out the notes, there's a typo in it, but it's fixed in the slides. This is not lambda, but gamma. So if for gamma equal 1, we can forget about this term, so we have simple intensity. If we have less than 1, we have inhibition. If we have larger than 1, we have clustering or aggregated patterns. So in modern point pattern analysis, you have locations of events, you have covariates, you have variables that characterize these events. You use kernel approaches to move from points to areas, and you bring these kernel estimates into the process to end up with an estimate of the gamma and the beta. And then given that estimate and some measure of the precision of the estimate, you can say this process is clustered, this process shows inhibition, this process is homogeneous or it's heterogeneous. So that is where modern point pattern analysis is at, and it's actually a very powerful way to move from aerial data in these kernel things here to point data, to event data, which are put at particular locations. Now, we'll just scratch the surface. As I mentioned in the first lecture, each of these topics is a whole course in its own right. And so you could easily spend a whole semester on just this, the estimation of these kinds of processes. You know, parametric, non-parametric, different kinds of GIP sampling, metropolis, and so forth. So that is where, if you wish, the action is in modern point pattern analysis.